Hello and welcome back, and here are the three units of calculating the temperature. We have degree centigrade and degree Fahrenheit and Kelvin. If we compare between degree centigrade and Fahrenheit, we'll find at the 0 degree centigrade it corresponds to 32 at the Fahrenheit scale, while the boiling degree of water, which is 100, corresponds to 212. So every 100 in this scale corresponds to 180. So if I want to find the corresponding Fahrenheit degree of a degree centigrade, for example the 50, so I'm going to deduct minus the 0 and divide by 100. I will add multiplied by 1.8 and add to 32. And here is the relation: degree Fahrenheit is equal to 1.8 multiplied by the corresponding degree centigrade, which I want to convert into Fahrenheit. I will add 32. While for the reverse, if I have a degree Fahrenheit, I have to deduct 32. Then I will divide 1.8. And since our degree centigrade is 0, so we will add to 0, we will get the corresponding degree centigrade. There is another unit which is called temperature in Kelvin. If we compare it between degree centigrade and the Kelvin, we'll find that the 0 corresponds to 273.15, which is the freezing point of the water. This is the 0 and this is the corresponding Kelvin. This is the boiling points of water. 100 degree centigrade is equal to 373.15. So every 100 of here corresponds to difference of 100 Kelvin. So this is the base unit of temperature in the International System of Units SI. There is an example: a metal rod of 7 meters is being heated to 35 degrees. The room temperature was 27. It means that my original temperature was 27 and it becomes 35, so an increase has occurred. The requirements is the amount of the expansion. If the alpha is 13 multiplied 10 of the power minus 6 per degree, it is a direct multiplication. The L naught is 7, which is here, and the difference will be 35 minus 27, which is 8, and then we'll multiply by alpha, which is 13 to the 10 of power of minus 6, and we'll find here that the expansion is 0.0027 meters. How the thermal strain causes stress. If the member is allowed to get expanded, then there is no problem like this degree. But life is not that easy. Sometimes you are not allowing the expansion by introducing fixed point here. So when there is an expansion, there is another opposite force will cause that expansion to be confronted. And we will consider the same piece of wire used before with both ends restrained, undergoing a temperature rise delta T. Since both ends of the wire are prevented from movement, stress is developed in the wire, forcing it to buckle. In order to find how much these stresses are and what parameters, first we have to consider the wire without restraint, and we'll get, as we have calculated before by using our equation, the amount of the expansion delta L. Now in order to oppose such expansion, we are assuming that there is a force returning back the expansion into L length. Now we push the right end and the wire to go back to its original length. This is the force that would have developed in the wire if both ends were restrained. As we know, the force will cause stress, and this stress is equal to B divided by the A, where A is the area of the cross section of this wire. Also, we remember that the Young's modulus of elasticity is the stress over the strain, while the strain is delta L over L. So we will make comparison and we'll find that the E is F over epsilon, while epsilon is delta L over L. So L will come up. So E will become FL over delta L, while we know that the delta L due to the thermal expansion is alpha delta T by L. L will go with L, and then we'll come back to this expression. This the stress we are looking for is equal to the E Young's modulus by alpha by delta T. The above equation shows the relationship between the change in temperature and the stress developed in the restrained structure. That is why we can say that the expansion, when it is not allowed, it is coming back to become stress. Thanks a lot and see you next time.